So I'm going to talk about the subset sum problem. I'm sure you all have seen it, but to be on the same page, let me define this here. So we're given a set x of n positive integers and a target number t, and we want to know whether some subset of these input numbers sum to the target. So for example, if those are your numbers and this is your target, then yes, there is a subset consisting of these three numbers that sums to the target. I'm doing a couple of simplifying assumptions here just to So we'll always assume that my numbers consist of only positive integers. Problem is a bit different if you also allow negative integers. I'm also saying that x is a set, not necessarily a multiset. So each input number can appear at most once, meaning that in particular the number of input numbers is bounded by t. So I can basically I'm only doing this to simplify asymptotic notation. I can throw away n sometimes. Well, you all know the problem because it's a fundamental in TCS. It's also studied in optimization and operations research. It's important because it's an NP-hard problem that is a special case of many other problems. So for example, the knapsack problem generalizes it, or integer programming generalizes it, and so on. And it has applications in crypto. As I learned a couple of days ago, many more applications than I thought. Anyways. So the regime, there are many different algorithms for this problem. The regime that I'm interested in this talk mostly is this pseudo-polynomial time setting, where the standard algorithm is this Bellman dynamic programming algorithm here. So which solves the problem in n times t time by building this huge table, and the I, s entry of this table stores whether some subset of the first I numbers can sum to s. When can this happen? When can the first I numbers sum to s? When is there a subset of the first I numbers summing to s? Well, either this subset does not include the ith number, then already among the first I minus 1 you can sum to s, or that subset does include the ith number, then among the first minus I minus numbers you can sum to s minus xi. And those are the only two options that you can have. So you can fill each table entry in constant time, right? So you can build this huge table in time proportional to its size, which is n times t. So in running time order n times t, we can solve subset sum. It's this classic dynamic programming algorithm, which I'm sure many of you have seen, which we use in undergraduate courses to teach subset sum. Now, you can wonder whether this algorithm here is optimal. And I'm working on fine-grained complexity, so of course I started working on this problem by trying to prove a lower bound. But there were actually also a lot of people trying to improve this kind of algorithm. So in the beginning there were more or less small tricks, let's say. For example, if you work on the word RAM model, so you can handle W bits at once, then you can basically shave off a factor W of this running time. This is a relatively old result. The first real breakthrough was by Karl and Xu in 2015, who showed that you can reduce this factor n to just basically root n. And I'm hiding some polylogarithmic factors here. So n times t is not the optimal running time. You can actually shave off. And then I worked on this problem and reduced it further down to near linear in t. More precisely, that's t log to the 4 t log n, some number of log factors. The big difference here is that all the previous algorithms were deterministic. My algorithm is randomized, which with some tiny error probability, let's say 1 over t. And then later this has been optimized in terms of the log factors. So Jin and Wu, they came up with a pretty different algorithm with the same kind of running time guarantee and a few less log factors. Right. So throughout the talk there will be a couple of open questions that I don't know how to answer. So for example, how to de-randomize this kind of algorithm here, I don't know how to do. But at least for randomized algorithms, well, n times t is not the optimal running time. Near linear in t could be the optimal running time, right? So maybe this is optimal now. Can we show a conditional lower bound, ruling out faster algorithms than t? And that's where fine-grained complexity comes into play now, finally. So Yeah, so I will not talk to you about these algorithms here because I mean lots of people here have already seen how this works. I mean, yeah. Anyways, so let me focus on whether we can show that this running time should be optimal or not. So classically in TCS, what do we do to show that the problem is hard? We show that it's NP hard, right? And like my view on like this P versus NP is like, I mean, we basically treat it as an axiom that P is not equal to NP, right? That satisfiability is not in polynomial time. If you treat this as an axiom and you combine it with reductions from satisfiability to lots of other problems, then what you get are super polynomial lower bounds for lots of other problems, right? Based on this axiom, you can rule out polynomial time algorithms for lots of problems, so you get super polynomial lower bounds. In particular, like subset sum was among the first like 20 or so problems that Karl showed to be NP complete. And if you like take his reduction and combine it with this axiom that satisfiability is not in polynomial time, then you get that subset sum is not in polynomial time. And precisely this means that it's not in time polynomial in n and log of t, right? Because the input size is just, well, you get n numbers, each number is between 1 and t, so you can specify it using log t many bits. So the input size is n times log t. And well, NP hardness rules out that you can do this, or P not equal NP rules out that you can do it in polynomial in n and log t time. Now, that's pretty far from the upper bound that we have. If we want to have a higher lower bound, we also need to start from a stronger axiom. And one of the common stronger axioms is the exponential time hypothesis, which states that satisfiability is not in sub-exponential time, so not in 2 to the little o of n time. That's what Impagliazzo and Paturi phrased as a hypothesis. And if you start from this, if you use this as an axiom, and again combine it with appropriate reductions to other problems, then you get lots of lower bounds that are tied up to the right constant in the exponent. Right? Here, the axiom already doesn't tell you what is the right constant in the exponent, so you also cannot expect to get the right constant for other problems. But up to this constant in the exponent, you can get many matching lower bounds. And indeed, people did that. So there are 2 independent works that devised such reductions to subset sum that show that you cannot solve the problem in time t to the little of 1 times 2 to the little of n. Which is already, I mean, which is the right time bound, except that we don't know what are the constants in the exponent. Because you can solve subset sum in exponential time, 2 to the n over 2, where meet in the middle. You can also solve it in time t, and you cannot reduce this to t to the little of 1, 2 to the little of n. Right? Now, I'm usually looking at these things even more closely, where I also want to have the right constant in the exponent. If you want to do this, then you need to start from an even stronger axiom, which is called the strong exponential time hypothesis. Which, like, roughly speaking, it states that satisfiability, well, the fastest known algorithm that we have for satisfiability is something like 2 to the n times polynomial factors. And the strong exponential time hypothesis, it states that you cannot reduce this basis of 2 to the n, you cannot reduce it to 1.99 to the n. More precisely, it states this here, if you want to know the true definition, it's this, that it's a statement about k-sat. Precisely for any epsilon that you pick, there exists a case such that k-sat cannot be solved in 2 to the 1 minus epsilon. Anyways, so if you start from this even stronger axiom, again combine it with appropriate reductions, then you can actually get lower bounds that are tied with the right constant in the exponent. And this is what Amir and Danny and Stvi here now? No? Okay. Well, what we did some time ago for the subset sum problem, showing that at least this time t is the right running time. So if you would improve the running time to t to the 1 minus epsilon times t to the little of n, then you would break this strong exponential time hypothesis. And I would read this as, I mean, we know how to solve the problem in near linear time in t, If you want to get sublinear time in t, then you have to pay an exponential factor in n. That's what this is stating. Okay, and that's one example of this huge landscape of fine-grained complexity lower bounds. Like most of what I have on this slide here are polynomial time problems. I will talk about this NP-hard subset sum problem throughout the talk, but the techniques are pretty similar. And this is one example in this blob of Seth-hard problems, so where we have lower bounds based on the strong exponential time hypothesis. And there are other hypotheses that have been used, like three-sum or all-pair-Schroders path, from which you can also show like lower bounds. And the ultimate goal, like if you work on fine-grained complexity and algorithm design, the ultimate goal is to get these kind of conditionally best possible algorithms. So you design some algorithm running in time, some running time, T of n, and you prove a conditional lower bound ruling out T of n to the 1 minus epsilon. Then you know that this running time is really best possible, right? In some sense, right? I mean, with some fine print, of course, because well, they could. I mean, all of this is in the worst case. So, like, who knows what happens on practical instances? It's only up to lower order factors. So typically, like, we rule out that you can decrease the exponent by a factor 1 minus epsilon. Typically, we don't rule out that you can, for example, have additional log factor improvements. So up to lower order factors is typically how precise we work on these. And all these lower bounds only work, they only hold under some complexity theoretic assumption like this strong exponential time hypothesis. So up to this fine print, I mean, this area allows you to design best possible algorithms in some sense. Right, and this is one example of such a best possible algorithm because we have running time near linear in t, and we know that if you want to decrease the running time to sublinear in t, then you need to pay an exponential factor in it. Let me also briefly mention that like a similar lower bound was known before under something that is called the set cover hypothesis. So Seth is the more standard assumptions. Set cover hypothesis is a bit less explored. But basically what this is telling you is that subset sum is a really hard problem. If you find a faster subset sum algorithm, you immediately falsify two conjectures of fine-grained complexity on satisfiability and on set cover. Okay, so far so good? That's will be the second part of this talk. Okay, so I want to give you like a brief overview about how such a lower bound here can be proven. Right, so I will start from just an NP hardness proof for subset sum. I mean, I'm sure you've seen some NP hardness proofs for subset sum. This one is a little bit non-standard, but it's just an NP hardness proof. Okay, so we reduce from satisfiability. So imagine that we're given some kind of CNF formula, and we want to construct a target number t, and then we want to construct input numbers. We will have one input number for each variable x in our formula, and assignment alpha to that variable. So alpha is just a bit. So this would specify that we want to set variable x to bit alpha. And then we will also have one input number for every tuple like this. So that's a clause of our formula and a satisfying assignment of that clause. Right, so alpha 1 to alpha s, those are bits that specify one assignment to the variables appearing in that clause, and I'm only looking at these such assignments that satisfy the clause. Okay, I will need a couple of helper bits. In like the first bit block, all the items will just have number 1, and the target will have number n plus m, which means that in total, I have to choose n plus m items. Then I have a couple of more helper bits, where like 1 bit for every variable and 1 bit for every clause. And naturally, like an item corresponding to variable x will just have a 1 at the position corresponding to variable x. and an item corresponding to clause C will just have a 1 at the bit corresponding to clause C. And I mean, those are just some bookkeeping bits. And if you think about it, all they do is that they make sure that you have to pick exactly one variable item for each variable and exactly one clause item for each clause. Right. And there will be a couple of more bits back here. That, right. But just these bookkeeping bits here together just ensure that for each variable x, we pick one such item here. So we pick one assignment to each variable x. And for each clause C, we pick one such item here. So we pick one satisfying assignment for each clause. Well, we're nearly done here, right? Now we have, I mean, we picked an assignment and it satisfies all the clauses. The only problem is that it doesn't have to be consistent yet, right? So what's left to do is to enforce consistency of all these assignments. How do we enforce consistency? Well, we will have a couple of blocks here, one block for every variable. And inside this block, if the clause item, if you have a clause where this variable xi appears, then you will just write down the assignment to that variable. So the clause item just puts 0 or 1 here, depending on what it assigns to that variable. The variable item wants to set like minus its degree times its assignment, so either 0 or minus its degree. And because, I mean, negative numbers are a bit weird here, I just add this d to make it a positive number, and then the target should also be d. So what does it mean? So if you just look at one block here, you have like this one variable item which is either 0 or minus its degree, and then you have degree many clause items, and each one has either 1 or 0. And this can only be consistent if all of the clause assignments are the same, and actually the same as what the variable assigns to it, right? So if, for example, so I mean, this here is either 0 or minus dx. If not all the degree many clauses pick the same value, then you can never get 0 or dx. They all have to pick the same value, and they also have to be consistent with the variable. So some very simple consistency check. And that's enough to prove NP hardness of subset sum, right? It's not the standard proof of NP hardness, but it's one relatively simple NP hardness. Now, from here, we want to go to set hardness. What does it mean? It means that we want to adapt this reduction to ensure this here, to ensure that the bit length of all the constructed numbers is about n, like 1 plus epsilon factor larger than n. Why do we want that? Because then we can rule out such an algorithm here, right? Because if we would have such a fast algorithm, well, then just plugging in this bit size here, we would get an algorithm that is faster than 2 to the n, so something like 2 to the 1 minus epsilon n. Right. So if we would get such a very small bit length, then we could rule out such fast algorithms for the subset sum problem. So that's our goal. Well, where are we at with this kind of reduction? Well, we need lots more bits, right? We already need n bits, n plus m bits for these kind of bookkeeping bits here. And then we have, I don't know, log n plus m we don't care about really, but then we have n blocks here, one for each variable, and in each one we have log of maximum degree of any variable many bits for that block. So that's the number of bits that we need so far in this reduction. So how do we get from here to here? Well, there are 2 ingredients basically, or I guess 3. The first one is just the sparsification lemma, and that's like the standard technical tool to use. So whenever you want to reduce from satisfiability, if you want to prove a Seth-based lower bound, you can always use the sparsification lemma, which allows you to assume that the number of clauses is linear, is order n, and the degree of each variable is constant. Right. So I mean, I'm not going to talk more about this. I'm just gonna assume that I can ensure this. But even now, I mean, like even just the first block of bookkeeping bits here, that's already n, and then we need some additional bits. So how do we get down to 1 plus epsilon n? That seems impossible, right? The second trick is that we block some variables together, right? So here we spend 1 bookkeeping bit for each variable. That's way too much. So let's just block like a large constant number of variables together and spend 1 bookkeeping bit only for every 100 variables together, something like this. So what happens then? So what am I saying here? So now, so let's think of a being some large constant, and I'm blocking a many variables together to form 1 super variable. So now each variable takes an assignment in 1 through 2 to the a. So that each variable consists of a many bits. Right. So I'm blocking together a variables. I'm also blocking together many clauses to form some super constraints. So now these clauses got somehow wider. They involve some more variables, and each variable is again now an a-bit string. And you can do this blocking to ensure that in total we now have n over a variables and n over a constraints, and all of these have a constant degree depending on this parameter a. This helps, right, because it means that like these bookkeeping bits that we have here, they got much fewer, right? We just have 1 bookkeeping bit for each super variable and each super constraint. Those are just n over a many, so if I pick a huge number a, then this is just epsilon, an epsilon fraction of n, so I can ignore it. So then the bookkeeping bits, they are fine now, just epsilon n. The issue now is with this consistency constraint. So before we had, each variable had assignment either 0 or 1, so we can just sum up the assignments and check whether this is equal to 0 or equal to the degree to check consistency. Now each variable has more than 2 values, and then summing up doesn't work anymore, right? Because if you sum up, if one item says that I want to assign 1, another one says that I want to assign 3, how can I distinguish this from both items saying that I want to assign 2? Right, so we do need some different consistency check here. And the consistency check that we use comes from additive combinatorics. And it's sometimes called k-sum-free sets. So what is this? A set S over some set of numbers between 1 and u. I call this k-sum-free if the following statement holds, that whatever k plus 1 numbers you pick in that set, if the first k numbers sum to k times the last number, then all of these numbers had to be the same. This is called k-sum free, sometimes k-average free, or whatever. Right, and it's very natural here, right, as a consistency check. It says, here is something that, that we can check with the subset sum instance. It's, some addition of elements has to be equal to something. So that's natural in the context of subset sum. And this here is that all of these variables are consistent, right? That all of them choose the same value. So it's very natural to use here. And there is a classic construction from 1946 due to Behrendt, which constructs very efficient k-sum-free sets. So think of k being a constant and epsilon being a super small constant. Then this says that that there exists a sum-free set of size n over universe almost linear in A, so n to the 1 plus epsilon. And you would find this kind of construction if you would look into such a book. This is the standard book on additive combinatorics by Terry Tao and Van Wu. This Behrendt, he worked on additive combinatorics, and this here is basically one easy counterexample to certain things that have been conjectured before in additive combinatorics. And so this was conceived as a counterexample to construct these kinds of K-sum free sets. And that's why you would also find it in this book to as an exercise to construct these kinds of sets. Anyways, but here we use them for hardness reduction. Right.
Your statement is about existential.
You can also efficiently construct it, but here we don't even need it because we only use this on constant size alphabet. So existential is even enough. Good. Right, and now, I mean, I will spare you the details of computing this stuff. I will just say that now here we plug in the K-sum free set for the consistency check. So before we wanted to plug in the assignment alpha I here. Now we just plug in the alpha ith number in a K-sum free set. And then if you look at one block here, one bit block, what you get is each clause chooses one element of a sum free set, and the variable item picks minus its degree times one element in the sum free set. And then if you think about it, the constraint that I'm expressing here is exactly the constraint of K-sum free sets. So if these things sum up to the target, then we are guaranteed consistency of these assignments, and then again we get we get correctness of this reduction. And I'm sparing the calculations, but if you go through with this, then you get really that the bit length is 1 plus epsilon n. The number of items that we construct will be something like order n. And then if you would have such a fast algorithm for subset sum, then you would break the strong exponential time hypothesis. Just as a rough overview. Any questions to that? Then let me get to right. So that, I gave you a rough overview over this lower bound here. I'm not going to talk about the algorithm, but together they form this kind of conditionally best possible result. Then let me get to Aviette's question, whether this kind of algorithm generalizes. Right, so the algorithm happened in 2017. The lower bound was published in 2019. It's already a little bit older. So there were a couple of years since then, and people try to generalize this in many different other directions, which is natural, right? Subset sum is very fundamental and central to many other problems. So naturally, you would try to generalize any lower bounds for subset sum. They generalize to many other settings. And as you will see, actually, that this lower bound that we have for subset sum, it's applicable to many other scenarios. And people looked at many other directions. In particular, whether this algorithmic improvement for subset sum can be generalized, and also leads to improvements for other settings. What you will also see is that, I've shown you one application of additive combinatorics here. You will see one or two more. So the application that we've seen so far was in hardness reductions, and in lower bounds in complexity theory, additive combinatorics has been used. As for example, there's at least one famous survey. About additive combinatorics from the TCS point of view, but none of this is about algorithms really, and there are only very few algorithms that make use of insights or theorems from additive combinatorics. One of the very few examples is this paper by Chan and Levenstein on which solves some special cases of three-sum faster using one theorem from additive combinatorics. And I will show you one more example of this form. Right. Right. And Aviat asked about the knapsack problem. That's one of the immediate generalizations of subset sum that we all know. Modular subset sum, that's subset sum, but I mean, you compute sums modulo some number m. It's also something that people studied. There are approximation algorithms for subset sum. You can look at other parameters. So not, I mean, here we studied it with respect to the target t. What about if we take the largest input number as a parameter? These are different directions. What I want to focus on mostly is this output sensitive setting. Right. Well, okay. What time is it? How much time do I have? 20 minutes. Good. Right. So what do I think? What do I understand as output-sensitive subset sum? So one of the typical tasks could be to list all the subset sums below some threshold t. So that's those are all the subset sums, and we want the ones that are below t. If you look at Bellman's classic algorithm, I mean, I claim to you that it runs in n times t time, but you can actually make it output sensitive in some sense. So you can, if you store this big table in a compressed way, so you only store the non-zero entries, then this actually runs in n times the output size time. So n times the number of different subset sums between 1 and t. Right, now here we had an algorithmic improvement. We could shave off this factor n of the running time n times t. So naturally, one question you can ask is whether you can also shave off this factor n from this running time bound of n times out. Or in other words, whether there is like a near linear output sensitive algorithm for subset sum. And I don't know, that's why it's like marked with this big Q here. I don't know whether there is a near linear output sensitive algorithm. We do have some improvements, but not near linear. Right, it's connected to this kind of problem here. So you're given two sets of numbers a and b and some threshold t, and you want to compute the capped sum set a plus b intersect t. What is that? So the sum set is this natural object here. Right? A plus b is just all the pairwise sums of an a and a, of an element a and an element b and b. That's the sum set a plus b. And it's, I mean, it's a very, very natural object in like subset sum because those are basically all the subset sums that pick exactly one element in A and exactly one element in B. Right, and because we are only interested in subset sums below T here, it now makes sense to look at the sum set, but we cap at T. We're ignoring all the sums that are above T. Right, now it's you can solve this in near linear time in T. That's not so hard, because I mean, sum set. I mean, you can solve this using fast Fourier transformation. Really, because if you take, I mean, if you take the indicator vector of A and the indicator vector of B, then their convolution gives you the sum set. So you can use fast Fourier transform to compute such kind of things here. And then if you're only interested at numbers below T, you can implement this in time, near linear in T. But now we want to... Yes, this O tilde hides like log factors. So this would be T log T actually. Right, so it's at most, N is at most T here, right? Yeah. But yes, I'm also hiding log N's, yes. Right, so, but here we are in this output sensitive setting. So now the question is whether you can compute this in near linear time in the output size. So you have given a sparse representation of a set A inside, among the numbers from 1 to T, and you're given a sparse representation of the set B. And now you want to compute this capped subset in near linear time in the output size. Is that possible? And here, I mean, now I'm really hiding like log factors, log n, log t, whatever. We also don't know that, really. What we do know is that if you can solve this problem, then you can also solve this problem. And that is really a generalization of the algorithm. So it's partly an answer to Aviat's question. So really, if you look at the algorithm that I had for subset sum, you can view it as a reduction from subset sum to sumset computation. And like, with a few more, like, if you, like, with a bit care, you can extend this to the output sensitive setting. And then you get this kind of reduction that if this kept subset sum is in time output size to the alpha, then also subset sum is in time output size to the alpha. And what we can also show is that this kept subset, we can do it in output size to the 4/3, but that's how we are right now. It's not, we don't know whether it's near linear, we don't have any kind of lower bound, and we don't have a better upper bound. That's where we are right now. Good so far. And some additive combinatorics comes into play. Let me give you some additional motivation for this problem here, because, I mean, why would you want to study this? It actually, so the algorithm that we get for this problem also solves the following problems in time k to the 4/3. So the one is, like, it's very similar still. The top k sumset. So you're given two sets of numbers. You want to compute the k smallest elements of the sumset, or alternatively the k largest elements of the sumset. This you can do in k to the 4/3, and it's really basically the same problem. There's like a binary search between the two. Like the more interesting problem probably is this one here. So top k polynomial multiplication. So you're given two sparse polynomials, and let me assume that they have non-negative coefficients, because otherwise they are cancellations, which makes everything very ugly. Okay, so sparse polynomials with non-negative coefficients. You want to compute their product, but you're not interested in all the monomials. You only want to have the k largest, the k highest degree monomials. How fast can you find the k highest degree monomials in a product of two sparse polynomials? And that's a generalization of this kept sumset problem. And we can solve it in k to the 4/3 time. We don't know whether it's faster or whether there's a lower bound. Okay, so this just as a little bit more additional motivation why it makes sense to study this problem. Okay. Now, okay, so what's the easy algorithm for this problem? So first of all, we can assume that the input size is at most the output size. So why can we assume that? So if we have a number in A such that A plus the minimum number of B is already larger than T, then we can certainly remove A. A is not part of any output sum. If we do this, then every number in A actually also corresponds to some sum in the output, and in particular, like any number in A plus the minimum of B, all these numbers here are different and are part of the output. So the output size is at least the size of A, and symmetrically the output size, you can assume it also to be at least the size of B. Now once we have that, we at least get some naive algorithm, right? You can certainly compute the sum set in quadratic time and just time A times B. You enumerate all the pairs. Compute this in time A times B, and now because A and B are small, we get output size squared. That's the very naive algorithm how to solve this problem.
So A and B.
Yeah, you compute all the pairwise sums, sort it, remove duplicates, and just keep the ones that are less than T. Yeah. So what I will show you is like one classic ingredient that leads to output size to 1.5, and then one additive combinatorics ingredient that gets to less than 1.5. And so what we can actually achieve is 4/3 as an exponent, but I won't show you all the details of that. And as an illustration, I will always use this thing here. So this here corresponds to the set A sorted from smallest to largest, and this here is the set B from smallest to largest. And then every point in this table corresponds to the sum of an element in A and an element in B. And I mark this sum green if it's at most T, and I mark this sum red if it's more than T. Okay, so right, so let's try to improve this algorithm here, and the strong ingredient that I will use here is the following: that without the capping at t, if you just want to compute sum sets, then you can actually do this in output sensitive time. That's a classic result by Karl and Hariharan. They did this a bit more generally for convolution, but an implication of their result is this: that you can compute sum sets in randomized near linear time in the output size. Right now, if you see this, first thought might be that doesn't it already do it? Not really, right? Because if you're given two sets A and B, it could be that most of their sums actually lie above t. And if we want to measure the running time in terms of just the sums below t, then we cannot simply run this kind of algorithm. Right, so it doesn't give anything. If you just use it naively, it doesn't give anything. So we will use it a bit more and a bit more. It doesn't give anything immediately. Second thought might be, well, if they manage to do this for A plus B, just look into the algorithm and adapt it to this setting where you're only interested in the ones below t. It doesn't work either. You spent lots of time on that. It doesn't work. So what we do right now is that we use this here as a black box, and I will show you how to use it as a black box. Right, so we split A and B into groups. So let's say we split A into 5 groups and B into 5 groups. And now I'm marking a group. I mark it green if all the sums in that group are below t, and I mark it red if all of the sums in that group are above t, and yellow are the boundary pairs, boundary blocks. So where some pair is below t and some pair is above t. Right. Now the red blocks we can ignore, right? We can check. We check their minimum elements, see that it's already above t, so we can ignore the whole block. For each other block, we need to compute the sum, and we do this in the most naive way. We just run this ingredient here on each green and each yellow block, right? Okay. So those are the blocks that are green or yellow, and then on each one we just run this first ingredient here, which gives this sum set AI plus BJ, and we move everything above t, and we take the union of everything that we computed. Now, what's the running time of this? So every green block here, that's part of the actual output, right? So the sum set size of a green block is at most the output size. So we can somewhat charge the running time that we spend on green blocks, we can charge it to the output size. And more precisely, we can look at the green diagonals. This is one diagonal here. And within a diagonal, because A and B are sorted, all the sums in here are less than all the sums in here. So they form disjoint parts of the output. So the total size, the total sum set size along the diagonal is at most the output size, right? That's what I'm using here. That there are about g many diagonals, one for every group, 2g, I guess. And within each diagonal, the total sum set size is at most the output size. And because this is also the running time that we spend on this, well, this is the total running time is g times out here. Right? G many diagonals, each one takes time out. And then we have the boundary blocks, and there we just do the easy brute force algorithm. Along the boundary, some pairs are larger than t, so we cannot charge to the output size. But we can say that certainly the sum set is at most quadratic, and because we split into g groups, this is the product of the two sizes, and because we have g boundary blocks, this is the total time over g boundary blocks. Now we have two things that are trade-off against each other. So basically what is happening here is that if you have a large number of groups, that means that the the boundary gets thinner and thinner, so you spend less time on the boundary. But if you have a large number of groups, then you get more and more diagonals, and within each diagonal you could recover each output element once in each diagonal. So you can, okay, and then you trade off these two running times that we get here, and this is the final running time that you get. Right, so I mean, to do the trade-off, you should actually pick the right G, but you can just run a couple of run it for a couple of values of G in parallel, and then you will get this running time. I don't see how to do that. No. I mean, it doesn't improve the running time. Let's say. Yeah. Right, and then, I mean, because A and B are at most the output size, this here is at most output size to the 1.5, so as I claimed. And if you look at just the green bounds here or just the yellow bounds here, these running times, they're actually tight in isolation. So this here can take this much running time, this here can take this much running time. The weird situation in this, for this number of problems is that it's hard to say whether together this can appear. So whether saying whether there are sets of numbers that realize these running times, or even for this specific algorithm, is pretty hard to tell. And in particular, I mean, there are reasons because this cannot happen together like this. So, like the ingredient that we use here is this Rouja's triangle inequality. And it says that not everything can happen with numbers. It says that if you have two sum sets that are small, then the outer sum A plus B cannot be too large. So we use it in this way here. So a simple application of this shows that shows this lemma here. So what does it say? So this sum set here is the smallest x elements of A and enters B, if all of them are green. And this here is the whole A and the smallest y elements of B. So if all of them are green, then we can bound the total sum set A plus B in terms of the output size and this x and this y. Well, whatever this says exactly, but it excludes certain situations, right? That a lot of stuff is green here, a lot of stuff is green here, and nevertheless there are lots of different sums here. This is, in some sense, this is excluded, and I will skip the proof, but it's really just two invocations of this triangle inequality. Okay, now final slide for this algorithm. How do we, that's the proof of concept now that additive combinatorics gives something in this setting. Okay, so we want to solve this problem. We choose x and y as like sublinear in the output size to 1 plus epsilon. And we look at three subproblems. So the first one is whole of B and the smallest y elements of A, and whole of A and the smallest x elements of B. And then, there might be a bit of green stuff left over here, and we just take the smallest rectangle here that covers the remaining green stuff. So given A and B, you can compute these three rectangles here. You can compute them efficiently. And then I'm saying that we want to solve these three subproblems here. Why can we solve them fast? Well, the first one here, we just run the previous algorithm. Why is it faster now? Because artificially I made one set smaller. I said that we take a sublinear number x and y. So the size of this new set B here is sublinear, and because the previous algorithm depended on the size of these sets, we now get something that is faster than exponent 1.5. Okay, so those are the outer two problems. What about the inner one? Well, the inner one has this whole thing here green, and this whole thing here green. You can see it from the picture. So you can use the lemma to argue that this whole thing here is a small sum set size. I mean, how do we compute this thing? We just compute this sum set here using this Karl and Heron algorithm, this ingredient 1. And the sum set size of this is bounded due to the lemma by output size over xy. And xy we chose basically linear in output size, so this here is basically linear in the output size. And I mean, you optimize over epsilon to get output size to 1.4. So really just a very simple trick of splitting the problem into 3 parts and running the previous algorithm or using this kind of lemma here. So it's basically a proof of concept that with additive combinatorics you can further improve this running time. I claim that, I mean, we can even get this exponent 4/3, but that's much more complicated than just this one call. Anyways, so now I spent basically all my time on this first direction, the output sensitive stuff, right? There are lots of other things. I should end, I guess. Yeah, no, let me just skip all this then. Right. Let me just brag about this here very shortly. I mean, there are lots of open problems here. I mentioned a few. There were a couple of more I had to skip. I mean, we study those open problems in this grant that I have since last year now, end of last year. Right, which is basically about like new algorithms as well as conditional lower bounds for this subset sum, knapsack, convolution type problems that they've shown you, and so on. And the big theme is that basically what I'm doing right now is reading this book and trying to understand the tools and use them algorithmically, because this has been done only like very rarely. Like this Chan and Levenstein paper is one example. I've showed you one more example where like Ruja's triangle inequality gave an algorithmic improvement. And yeah, basically this is about studying how this works, and then also trying to generalize this to like classes of integer programming problems. So yeah, let me know if you're looking for a postdoc position, and let me stop here.